When people hear the word motion, they visualize something obvious: a car rushing past, a ball arcing through the air, a hand shifting from one place to another. It feels so fundamental that it barely seems worth examining. Things move, end of story. Except it's not the end, because the instant you pose a slightly sharper question, moving compared to what, the ground crumbles beneath your certainty. Look around yourself right now. You feel stationary. The room feels stationary. Nothing dramatic appears to be unfolding. Yet the earth is rotating beneath you at hundreds of meters per second. Simultaneously, the earth is hurtling around the sun, and the sun is orbiting the galactic center, and the galaxy itself is drifting through an expanding universe. All of that motion is occurring while you sit there sensing perfect stillness. So which description holds truth? The unsettling answer is all of them. Motion does not belong to an object in isolation. Motion belongs to a relationship. It exists only when you compare one thing to another. Remove the comparison, and the question, is it moving, loses meaning entirely. That single realization quietly replaces an ancient picture of the world. For centuries, people imagined motion as something absolute, as if the universe possessed an invisible grid marking what counts as genuinely moving and what counts as genuinely still. Physics abandoned that picture, not because it became unfashionable, but because nature refused to cooperate with it. Every experiment tells the identical story. You can describe motion only by selecting a reference: a train, the ground, the earth, the stars. Each choice tells a different, equally valid story. Physics keeps working in every single one of them. This already explains something you've felt your entire life without naming it. When an aircraft cruises smoothly, motion vanishes from awareness. No special sensation announces speed itself. Only changes in motion, starts, stops, turns, make themselves known. The body responds to acceleration, not motion alone. That observation proves to be a profound clue. It suggests that motion is less about where something is heading and more about how its state transforms. Speed becomes secondary. Relationships take center stage. What matters is consistency between descriptions, not a privileged viewpoint. Once you perceive motion this way, it stops being a simple idea and starts functioning like a principle that organizes all of mechanics. It connects walking across a room to planets in orbit, and it accomplishes this without ever asking who gets to be really at rest. That question fades away, and a superior one takes its place, one that pulls you forward because answering it reshapes how every movement in the universe is understood. And once that idea settles in, that motion belongs to relationships rather than objects. We can finally dissect it carefully and see how it actually operates without leaning on intuition, where intuition tends to mislead. Think about a train traveling along a straight track at constant speed. Inside the train, someone stands up, tosses a ball straight upward, and catches it again to the person on the train. The ball rises and falls in a straight line. Nothing surprising occurs. The motion feels ordinary. Now imagine observing that same event from the platform as the train passes by. From there, the ball follows a curved path through the air. It moves forward along with the train while simultaneously moving up and down. Two observers, two different descriptions, one single event. Neither description is more correct than the other. This example matters because it exposes a hidden assumption most people carry without noticing: the idea that there must be one correct account of how something moves. Physics relinquishes that idea. Motion does not arrive with a built-in label telling you which viewpoint is privileged. What matters is internal consistency. As long as measurements made within a chosen reference agree with each other and obey the laws of physics, that description stands on equal footing with any other. This is the central mechanism behind motion in physics. Motion is the change of position relative to a chosen reference as time passes. That sentence may sound plain, but every word carries weight. Position requires a coordinate system. Change requires comparison. Time provides the ordering. Remove any one of these and the idea stops functioning. This explains why the question, "Is it really moving?" leads nowhere. Really compared to what? Compared to the ground? Compared to the sun? Compared to the center of the galaxy? Each answer produces a different number, and none of them cancels the others. This is where everyday intuition collapses. Daily experience suggests that motion should announce itself. Something moving should feel different from something at rest, yet constant motion produces no internal signal. A smoothly moving train, plane, or spacecraft behaves identically to one sitting still, provided no turns or speed changes occur. Physics does not find this surprising. Common sense does. What stands out instead are changes in motion, sudden starts, sudden stops, curving paths. These events create sensations, forces, and measurable effects. The body responds to acceleration, not to motion itself. That distinction explains a great deal. Early thinkers believed motion required continuous effort. If pushing stopped, motion should fade away. That belief felt obvious because friction is everywhere in ordinary life. Floors, air, roads, and materials constantly interfere. Once friction is accounted for, the picture changes. Remove interference and motion persists on its own. Objects in space continue moving for enormous distances without slowing. No force is needed to keep them going. Force enters the story only when motion changes, when speed increases, decreases, or direction bends. From the viewpoint of physics, motion is not something that must be maintained, it is something that must be altered. This is why the laws of motion are written the way they are. They describe how changes occur, not how motion exists. They focus on acceleration because acceleration reveals interaction. It tells you when something external is acting. At a fundamental level, motion is the natural behavior of objects in space and time. What feels like rest is simply a shared motion between you and your surroundings. Once this idea is accepted, many familiar puzzles dissolve. Why does a dropped object fall straight down inside a moving vehicle instead of landing behind you? Because it already shares the vehicle's motion before it is released. No invisible push is required to keep it moving forward. Motion continues unless something interferes. Why do passengers not feel Earth's rotation? Because everything nearby shares that motion as well. Without a difference to compare against, motion leaves no trace. This relational nature of motion also explains why physics places such importance on reference frames. A reference frame is not a physical object, it is a bookkeeping choice. It defines how positions and times are labeled. Change the frame and the numerical values change, but the underlying behavior remains consistent. Physics does not search for the correct frame. It demands that the rules connecting frames agree with each other. At everyday speeds, those connections are simple. Velocities add in a familiar way. At very high speeds, the connections become more involved and space and time begin to intertwine. But the core idea remains untouched. Motion has meaning only within the chosen reference. Now it becomes possible to say what motion is, not just what it does. Motion is a description of how spatial relationships evolve over time under the constraints imposed by the laws of physics. It is not an ingredient added to objects. It is not a force acting upon them. It is a way of accounting for change. That description might sound abstract, but it is grounded entirely in measurement. Positions are measured, time is measured, and motion is the comparison between them. And this leads to an unexpected conclusion. Motion is not something that happens inside space. It is part of what gives space and time their physical meaning. Without the possibility of motion, space would have no operational definition. Without time, change could not be ordered. Motion ties them together. Once this is understood, talking about motion becomes easier, not harder. One no longer asks whether something is moving in an absolute sense. One asks how it moves relative to a chosen reference, how that motion changes, and what interactions are responsible for those changes. That framework is powerful enough to describe falling objects, orbiting planets, flowing rivers, and light crossing the cosmos. It does so without invoking hidden backgrounds or privileged viewpoints. And it leaves you with a question that naturally follows, not as a tease, but as a logical consequence. If motion itself carries no special status and only changes in motion to reveal interaction, then what exactly governs those changes, and why do they take the forms they do? That question does not step away from motion. It grows directly out of understanding it well enough to explain it to someone else. Once motion is understood as a relationship rather than a possession, the consequences begin to accumulate, and some of them run directly counter to how people expect the world to behave. One of the first surprises is this: motion by itself does not explain anything. It describes, but it does not cause. Knowing that something is moving tells you where it is relative to something else as time passes, but it does not tell you why it keeps doing so or why it ever changes. That role belongs to interaction. This immediately overturns a common mental picture. Many people imagine motion as something fragile, something that needs constant support. Physics finds the opposite. Motion persists naturally. What requires explanation is deviation from it. This leads to a result that feels backward at first. A force does not give an object motion. It gives an object change in motion, speeding up, slowing down, turning. These are the signatures of interaction. Motion itself is the default state. Once this is seen, the universe begins to look less like a collection of moving things and more like a web of relationships that remain consistent unless something interferes. Here is where a paradox often appears. If motion is always relative, how can effects that depend on motion be real? How can collisions matter? How can energy transfer matter? How can momentum be meaningful? The answer is that while motion has no absolute owner, relationships do. When two objects collide, what matters is their motion relative to each other, and that relationship determines outcomes. It determines how momentum is shared, how energy is redistributed, and how directions change. No observer disagreement erases those results. Different observers may assign different speeds, but they all agree on what happens next. This agreement is the hidden backbone of physics. It is also why motion connects directly to deeper principles. Conservation of momentum, conservation of energy, and the structure of forces all rely on the same relational idea. They do not depend on absolute motion. They depend on consistency across descriptions. Once you see this, a surprising unification appears. Motion, inertia, and force are not separate topics. They are different ways of talking about how change is constrained. Inertia describes resistance to change. Force describes the interaction that produces change. Motion describes how position evolves when change occurs or does not occur. Together, they form a single story about how the universe manages change without contradiction. This also explains why time plays such a central role. Motion cannot be defined without time, and time cannot be measured without change. A clock is not a device that detects time directly. It detects regular motion or regular change. Time gains meaning through motion. This creates a deep link between motion and causality. Causes precede effects because motion orders events. Without ordered change, cause and effect collapse into confusion. Now consider a result that feels unsettling until it is fully absorbed. If motion has no absolute status, then rest has no absolute status either. Being at rest is simply sharing motion with nearby objects. This means the universe does not privilege stillness. Stillness is not special, it is merely common motion. This matters because many everyday explanations rely on an imagined background of rest. Physics does not use that background, it uses relationships instead. From this perspective, even large-scale motion loses its drama. The Earth's movement around the Sun is not something that must be justified by an external reference. It is a relationship maintained by interaction. Remove the interaction, and the relationship changes. This brings meaning into focus. Motion is not about where something goes in an empty arena. It is about how relationships endure or change under constraints. Those constraints are the laws of physics, and they exist to ensure that no description breaks consistency with another. This is why physics places such weight on symmetry between observers. If the laws favored one viewpoint over another, motion would become arbitrary, explanations would fracture, prediction would fail. Instead, the universe enforces agreement. Once motion is seen this way, its meaning becomes clearer without becoming mystical. Motion tells us that the universe allows change, but only in ways that remain compatible across all valid perspectives. It allows variety without chaos. It allows difference without contradiction. This also reframes how we think about explanation itself. To explain motion well is not to say this thing moved because it was pushed. It is to say, given these relationships, these interactions, and these constraints, this evolution had to occur. That kind of explanation does not rely on imagery. It relies on necessity, and that is the deeper consequence. Motion is not just a topic within physics. It is one of the conditions that makes physics possible. Without motion, there is no measurement. Without measurement, there is no law. Without law, there is no understanding. Motion sits at the base of the entire structure. So when someone truly understands motion, they no longer think of it as an everyday word describing visible movement. They think of it as a rule-governed description of change, anchored in relationships, protected by consistency, and woven directly into space and time. That understanding allows them to talk about falling objects, orbiting planets, flowing rivers, and accelerating vehicles using the same ideas without patchwork explanations. And more importantly, it allows them to explain motion to others without appeal to authority or memorized rules, because they understand what motion means and why the universe treats it the way it does. At that point, motion stops being something that merely happens. It becomes something that reveals how the universe holds itself together. Motion no longer appears as a simple topic placed at the beginning of physics for convenience. It stands out as a foundation that supports nearly everything else. In physics, motion does not describe an extra feature added to objects. It describes how relationships between positions evolve over time under rules that apply everywhere. With that perspective, ideas that might seem separate begin to form a single structure. Objects continue moving unless interactions alter their motion. Forces describe how motion changes, not how it exists. Mass measures resistance to changes in motion. Reference frames provide different descriptions without changing physical outcomes. These ideas are not independent statements, they reinforce each other. What physics truly knows about motion comes from repeated observation and testing. No experiment has ever identified absolute motion. Constant velocity cannot be detected from inside an isolated system. Changes in motion always reveal interaction. The same laws hold in every inertial frame. These are not philosophical preferences. They are conclusions enforced by evidence. Motion also connects directly to conservation laws. Momentum remains conserved because physical laws do not favor one position over another. Energy accounting remains consistent because motion evolves through time without hidden exception. These connections are precise and measurable, not interpretive. There are limits to what is known. Physics does not yet know whether motion can be explained by something more basic or in whether space and time themselves emerge from deeper structures. It is not known whether future theories will revise how motion is described or simply sharpen existing descriptions. What is certain is that any future theory must still account for the relational nature of motion and the absence of privileged viewpoints. This explains why motion appears everywhere in physics. It is not taught early because it is simple, but because nothing functions without it. Understanding motion this way simplifies explanation without oversimplifying reality. Falling objects, turning vehicles, orbiting planets, and traveling light can all be described using the same core ideas, applied under different conditions. The differences come from interaction, scale, and reference, not from separate rules. The practical takeaway is direct. Explaining motion does not require asking whether something is truly moving. It requires asking three specific questions: relative to what, over what time, and under which interactions. Those questions are sufficient to describe every case motion physics currently addresses. This approach replaces guesswork with reasoning. It allows motion to be explained clearly to others without memorized rules or appeals to authority. It also explains why physics works consistently across laboratories, vehicles, planets, and galaxies. Motion shows that the universe allows change while enforcing consistency across viewpoints. The consistency makes prediction possible and explanation reliable. Consider how this understanding transforms everyday observations. When you drop a pen, it falls. The simple description says gravity pulls it down. The deeper understanding recognizes that the pen follows the straightest possible path through curved spacetime, and down is simply the direction that curvature dictates. Motion has not changed. The framework for understanding it has deepened. When a satellite orbits Earth, the simple description says it's moving in a circle. The deeper understanding recognizes that it's falling continuously but moving sideways fast enough that Earth curves away beneath it. The satellite and Earth are engaged in a gravitational relationship, and motion is the language that describes how that relationship unfolds over time. When light crosses the universe, the simple description says it travels at constant speed. The deeper understanding recognizes that light follows paths through space-time, where space and time mix in ways that depend on the observer's motion. Yet every observer measures the same speed for light, demonstrating that motion's relational nature extends even to the most fundamental aspects of reality. These examples show that understanding motion is not about memorizing facts. It's about seeing patterns, recognizing relationships, and understanding constraints. It's about knowing why things happen the way they do, not just that they happen. This understanding also reveals why certain questions cannot be answered. What is the velocity of the universe? Has no meaning because there is no external reference against which to measure it. Is time travel possible? Depends on whether motion can be structured in ways that loop back on itself within space-time's constraints. What happens at the exact moment motion begins? Dissolves once you recognize that motion is continuous change, not a discrete event. The framework of motion also explains why approximations work so well in everyday life. Newtonian mechanics, which treats space and time as separate and absolute, produces accurate predictions for objects moving much slower than light. This is not because Newton was lucky or because reality changes at different speeds. It's because the relational effects that distinguish relativity from Newtonian mechanics become negligible at everyday speeds. The deeper truth contains the simpler approximation as a special case. This is why physics progresses without discarding earlier understanding. Newton's laws remain useful because they correctly describe motion within their domain of applicability. Einstein's relativity extends the description to include high speeds and strong gravity. Any future theory must do the same, extend the description while preserving what already works. Understanding motion at this level also clarifies why physics uses mathematics so extensively. Motion involves continuous change, and mathematics provides precise language for describing continuous relationships. Equations are not arbitrary symbols. They are compressed statements about how relationships must behave to remain consistent. When an equation says that force equals mass times acceleration, it's stating that the change in motion acceleration is proportional to the interaction force and inversely proportional to the resistance to change, mass. Every term has physical meaning. Every symbol represents something measurable. The mathematics is not decoration. It's the most efficient way to express the relationships that motion embodies. This brings us to a final realization. Understanding motion is understanding how to think about change itself. In physics, change is not arbitrary. It follows patterns. Those patterns can be described, predicted, and explained. Motion is the clearest example of this because it involves the most basic kind of change in position over time. But the principles extend further. Chemical reactions involve changes in molecular configurations. Biological processes involve changes in cellular states, and ecological systems involve changes in population distributions. In every case, the same fundamental approach applies. Identify what changes relative to what it changes, under what constraints the change occurs, and how those constraints ensure consistency. With this understanding, motion becomes something that can be explained everywhere. It appears using the same underlying principles. The explanation does not require invoking mysteries or accepting contradictions. It requires recognizing relationships, understanding constraints, and seeing how consistency is maintained across different descriptions. That is the value of understanding motion properly. Movement becomes something that can be explained universally, clearly, and completely not because motion is simple, but because its complexity is structured. And that structure, once seen, illuminates not just motion but the entire architecture of physical explanation. Motion is the language physics uses to describe how the universe changes while remaining comprehensible. Master that language, and you master the foundation upon which all physical understanding is built.